This is Anthony Wise. This is Mathematical Logic, course 5154. This is my problem presentations. I think I've got 8 to do today, so we're going to try to get through all of this. So we'll go to the next slide. So the first one is for models and ultra products, the Bell and Thompson book. This is page 75, example 1.6. The set R that we'll be talking about is the rational numbers, and the set S is the real numbers. And basically we want to show that the set R with the strict ordering operation, which is that less than symbol, is contained in the as contained in the set S, is actually an elementary extension into the set S. Or actually the way to say that would be that the real numbers as strictly ordered is an elementary extension of the rational numbers with a strict ordering. So here's the proof. So let R be the set of rational numbers, and let the set S be the real numbers. Let that less than equal, or that less than symbol be the usual strict ordering of these sets. So basically, if R is contained in S, which is given in the problem statement, then what I've written here is that for every A, for every basically term, that's what I'm using the A as, every variable in some text, for all, I should say for all, for all A's or all terms within the set R, there exists an A within the set S where the set R is an extension or is onto the set S. And thus this is an elementary extension of the set S. Basically what this means is that for every element, this first part, for every element that is in R, all of them, there's not a single one that's been left out, there exists at least one match. Basically that's what this, there exists at least one in the set S, so that R is onto S, and thus is an extension. S is an extension of R with this well ordered. And you can think about it like this for rational numbers, like 1/2. There is definitely a 1/2 in the set of all real numbers. And if you look at all the number sets together, the rational numbers is a subset of the real numbers. So that one's pretty straightforward. There's probably something else I'm missing that I need to write there, but that's what I have. So moving on to the next one. This is actually the last part of example 1.3. Again, this is on the set of rational numbers and real numbers. This one was a little more complicated because this is in the 3 bars is an elementary equivalent statement. So it's saying that those two sets are with the operation of a strict ordering, they are elementary equivalent to each other. This is kind of strange because the set of rational numbers is countable or denumerable, but the set of real numbers is not. There's a couple of proofs out there for that. I won't go into it, but that's just, in my mind, that's kind of funny to think about. So anyway, so here's the proof for this. And the book goes into a kind of a different proof for this, and I went back and forth on how to present it. This is mine. I really appreciate some feedback on it. So again, let R be the set of rational numbers, let S be the set of real numbers, and then let this less than symbol be the usual strict ordering of these sets. All that is given in the problem statement on page 74. Then the set R with the ordering is contained within the set S with the ordering, so that's also given. So basically what I have said here is that for all elements in R, there exists at least one element in S that maps from R to S, right? And so this is basically what we had before in the previous example, and that's what I'm using to prove this one. The difference is going to be here. So if this is the case, right, then for all elements in B such that S, such that the elements, there exists a formula that maps all the elements of B within S to an H of B within R. And that's basically just phi, right? So then if that's true, then for all B's in S, for all the terms in S, there exists at least one H of B within R such that the previous relation held, which is R onto S. So that basically means that if you have, you're going forward into S, so you're taking an A for all the A's in R, they map directly into S, and then there's a function phi that basically takes all of the S's or all of the B's in S and maps them back onto R, so that this relationship between the two sets is elementary equivalent. So, like I said, I kind of muddled that one up a little bit, but you get where I'm going. Some feedback would be greatly appreciated. So then the next one is from the Logic of Thermostatistical Physics. This is from page 23 through 25. Basically, it's talking about state spaces, and it starts to talk about this ideal gas under a quasi-static process. And so what I did here was it goes into some depth about how to impose some logic onto these and then and build up these relations. But it also talks about what happens if you have too simplistic a viewpoint. And so with this proof I wanted to kind of show that. So if we assume that time, t, holds and it is variant with these three related variables, which is pressure, volume, and temperature, right? Pressure, volume, temperature. And all these are variables that define the state of the gas at any given t, right? So from any of the thermodynamics class or fluids classes or even some of the chemistry, the ideal gas law basically is a formula that says if you vary two of these, you can get the last one. It doesn't matter which two you have, you can always get the third one. And so basically that's what I'm saying here. There is a formula phi where the relation holds. Then and basically for all of time, right? Because time is time is how you're stepping through your equation. There exists at least one variable v1 and one variable v2 that is within phi, such that there exists one variable v3 in phi where basically you can get a solution that is within your solution space, which is TH. And that is given within the book as well. And so, actually I need to update this to TH. So TH is the set of all possible solutions of phi. So if phi is your ideal gas law, it basically means that that is a set of numbers or a set period that varies with these three variables only, and that's it. And that all of the solutions that can come out of the formula phi are within this set of TH, right? So I'm saying thus, if you have a formula phi and you have variables 1, 2, and 3, and any one of and this formula given these variables, that solution is not within TH, then one of your variables, v1, v2, or v3, must be rejected. And it kind of goes into some depth about that in the book. And it talks about, if you have, if you're measuring for pressure and temperature, or for volume and temperature, or for pressure and volume, you have two of them, and then you get a third one through experimental means, and then you push it through the ideal gas law, and you get some kind of solution that doesn't hold. Then you have to go through your variables and say, well, I got this one here, and I can rely on this one here, and so the third one must be rejected. So my statement for this is that this is really too simplistic of a viewpoint, because the experimental data is really rarely going to follow a nice ideal formula. And so this logic will hold only for the ideal case, but many times when you're doing when you're getting experimental data, it's not the ideal case. So it's just kind of neat to think about that. Yeah, yes, you can impose this logic on there, but when you actually take it into the real world, this needs to be modified slightly so that you have some kind of idea about maybe a range of values you can get, and maybe that range of values is just outside this set of all possible solutions for your ideal gas law. So, okay. The next one is from pages 41 through 47 of the same book. This is actually going into my background a little bit. I had a fluids class and we talked about this in depth. It's kind of neat to think about, as it's kind of a rare case, but it is something that happens. So basically describe this as let T be a temperature, and if T is assumed to be the measure of average length variate of a Brownian motion excited by an amount of kinetic energy. Basically what that means is you have a molecule and you're measuring temperature of that molecule, but really your temperature is an average vibration of that molecule as excited by kinetic energy, right? That's really what you're measuring on a very, very small scale. Then a molecule of gas moving through a long confined channel will actually exhibit two different temperatures. And that's very strange to think about, but basically here is the logic behind that. Let M, or M is the set of measurable spaces, right? Whether that is, and that's a length or a dimension, right? And in this example, I'm doing X and Y. I left the third axis out, it's fine, but it works for this. So, and then let phi be this confined space, so that's kind of like your formula or your function that you're working with. And then A is the temperature as taken from the x-axis, so it's only one-dimensional. And A2 is the temperature taken from the y-axis, which is it's 90 degrees to that, so it's in the second dimension. So if you look at the logic here, basically it is for all, or sorry, there exists a phi within this measurable spaces, which means there is a confined space that is still measurable, and there exists a temperature 1 and a temperature 2 within these measurable spaces. Basically, the temperature 1 and temperature 2 is from these reference points, right? Such that the phi at A1 and A2 is not equal to the join of temperature 1 and temperature 2. And the way I define this part of it is the join between temperature 1 and temperature 2, the different viewpoints of the axes, is that without a confined space, your temperature 1 and temperature 2 are going to be exactly the same because the molecule is free to vibrate. But in a confined space, especially traveling through a confined space, your molecule it cannot vibrate enough because it's constrained. And so I made this a little note down here. By limiting the Brownian motion, the length variant is constrained in one of the dimensions and is thus providing difference in measurable temperature. And we actually see this especially at very, very high temperatures in very, very small spaces. So turbine engines, if you have a very small leak or a very small passageway, then this logic actually holds. Basically, it is taking, you could be measuring something and with your temperature probe in that area and you're within limits, and then whenever you actually run it, it's burning through your material because it's just above the limits of your material. So pretty neat stuff. So the lessons that I learned from these two texts, which are the main texts for the course, is that a relation can be an elementary extension of a space, but if it is not onto, then it is not an elementary equivalence. So that's really, it's got to be 1-to-1 and onto basically in order to be a elementary equivalence. And then the second one is if the logic that is applied to a free space is too simplistic, that should be two O's, then this will result in an error for the truth values. And basically that means that you could run your logic, right? But if your state space logic is too simplistic, like the ideal gas law, and you get a variation in temperature or a variation in pressure outside of ideal limits, then your truth value will actually be false when it could be that is actually the observed condition. So, and then the third one is if you have a general feel for the underlying logic of the environment you are working in, whether that's a state space or that's a metric space or that's a set, the set of all reals or whatever it is, then there are some powerful truths that can be discovered, such as temperature can be directional, which is, that's outside the box right there. So, okay, so then the next one is a problem presentation from Proof Theory. This is from page 148. This is really just an example of partial versus total recursive function. And I actually like this terminology because it gives you an idea of the difference between the two. So I just defined a couple of things. Let fr be a recursive function. Let A be the set with elements A0 through AN, and let B be the set of elements B0 through BN. Just open sets basically. So a partial recursive function, basically the way that works is for all elements AN within A, there exists a Bn within B, so that the recursive function maps basically the AN into a Bn. But that does not mean that it maps it back the other way. You can see there's no double arrow here, and this right here is not a for all. It's a there exists one Bn, right? So then that's very different than the total recursive function, which is for all AN in A and all BN in B, right? Then such that there is a recursive function that maps AN, right? You put AN into the function and maps it to BN, or you can go BN back to AN. So double arrow for all BN. That's the difference. You're getting 100% of the variables from A to B, and then from B back to A. So, okay. So the second one, or the next one, is from page 170. This is a second order proof, and basically this is a really very, very simple one. I've been trying to kind of get my head around the second order stuff, and all these presentations have some form of second order logic in them, which is kind of neat. But so this proof is basically for all x's and all y's, right? We're going to say that x equals y, and that implies that if you have a function that has x, then it is elementary equivalent to the function with y. That's really easy to think about, where f is a formula. So like if you have x plus x, then x plus y is going to be exactly the same thing, right? So we assume, so I did this by contradiction, so we assume that for all x's and all y's that x is not equal to y, but it still implies this elementary equivalence relationship between the function x and the function y, right? Since we've already stated right here that this is an equivalence relationship, so if the function with x in it is an elementary equivalence to the function within that has a y in it, then there and I should actually say and right here, and copy this, x is not equal to y, then there has to exist at least one f of x that where this equivalence elementary equivalence does not hold. Basically, there's got to be at least one x where f of y does not hold, right? Which is pretty easy if you think about it. So by definition of an elementary equivalence, this has to hold for all cases, right? Thus, by contradiction, the statement holds. So, all right, the next one is from non-standard methods. This is just an example for for a bounded ultra power. I wanted to go through this because I wanted some feedback about this. I kind of understand this to mean one thing, and we'll get to that down here as a note. But anyways, I'll walk through this real quick. So from a previous problem presentation, I presented the hyperreals as denoted by R star, our extension of R, such that R star includes the infinite set of infinitesimals and their reciprocals, which are very, very large numbers, hugely, infinitely large numbers, right? So by definition, this V of R is a superstructure on R. And basically what it does is it maps R over and over and over so that you have some space to work with. So we're going to let U be an ultra filter on the natural numbers, right? And we're going to let A and B be two bounded sequences or subsequences of R. So if we let A be equivalent within this ultra filter of A is equivalent to B within this ultra filter, then that is if and only if the i's in A are basically such that A, it has to be equal to B. And all of that has to be within the ultra filter. So we're saying basically that that the ideals within A and B are exactly the same, and that set is all within the ultra filter. That's how I understand it. So basically I'm saying if the embedding of the superstructure on R is in the ultra filter is equivalent to the equivalent set, which is denoted by this subscript of the ultra filter, then this is also the case, right? Which is the equivalence class of A under the ultra filter U is equivalent to the equivalence class of B. So basically that leads itself into this right here. And this is really what the ultra power I think is all about, or to my understanding. You're basically mapping the superstructure as it maps into the superstructure into the ultra filter. And what this part right here does is specifically you're mapping this as a power set over and over and over into the ultra filter. So it's like if your ultra filter is 1, right, then you'd be mapping the set A, which contains 1, it's not empty. You'd be mapping it A over and over and over and over and over again. And so that's what I'm saying down here is the takeaway from this example is that the ultra power is a set, which is the equivalence class of A within the ultra filter, and it's mapped over and over and over and over again so that you have some space to work with, which is a part of that superstructure. This book has been kind of challenging for me to learn. The notation's a little bit different from the other books, and I'm really having to work at it. So feedback for this problem would be much appreciated. So then here's my takeaways, or my something I learned from the section texts, right? The first one is that the second order logic is either inconsistent or incomplete, and I think about this like as a part of this second one right here. Second order logic uses more than one order of quantifier, so it's like for all A's and for all X's, or for all X's and for all Y's, or for all X's there exists at least one Y or at least one Z. I think one of the examples in the book was that for all X's there exists at least one Y for all the Z's, such that X is equal to Z. So that's really the nature. And in class we've talked about this as the notion of a horse. So the first one is basically saying that you either have a horse or you don't, right? But a second order logic is for all notions of a horse, then X can either be a horse or it can't be a horse. And you can't really say that in first order logic. The other thing is that really the real world example for me is that this is like an embedded if statements within Microsoft Excel. So you have a set that you're dealing with that you impose this if statement on, and you're filtering it for certain values or a certain type of logic. And then within that if statement, you're saying if this part of this statement equals something, equals 0, equals 1, we'll say it's a filter, right? If that holds to be true, then there's this second if criteria, and then that's what you push through. So it's like a filter on a filter, right? And then the number 3 is the ultra power is a power set embedded in an ultra filter, and it acts like an identity. And in the non-standard methods book, it talks about on page, I think it's like 20, page 20, 18 to 20, somewhere in there. Someone can correct me on that. It talks about that when you map this superstructure into the ultra filter and as an ultra power, then basically what you're doing is kind of like building an identity set, and then you map that over into whatever extension that you're trying to do for your superstructure, so that you have that identity set within it. Because if you just map just the superstructure itself over into like an extension like R to R star, then you don't have the identity set within it. So you need both in order for it to be I think elementary extension. So any feedback would be much appreciated. That's all I have for today. I'm gonna post these right after this and put it up in the discussion forum. So thanks.